Great. Thanks to you guys for organizing this. It's been a very nice workshop so far, and I wish I could spend more time in Florence. Unfortunately, I have to leave on Wednesday, but yeah, I've seen maybe 10% of what's to see in Florence. It's very impressive. Um, yeah, so this is work. So basically, I'm gonna give a two-part talk. I would like to focus fully on new physics from galaxy clustering, but I've done with people, um, my group, we've done a lot of work on new inference approaches, and Massimo Pietroni gave a talk on this related stuff already last week. So I figured I should also cover a bit of that, and probably you will hear, if you're not familiar with this, you will hear a lot more on this. So maybe it's a good thing to review also. So this is the group of people who have been working on new inference. This is the group who's been working on new physics. I'll introduce them later. So, okay, so let's start with the inference problem, right? How do we do inference in cosmology? As a, you know, the most logical way to approach it is as a Bayesian, and to approach it as a Bayesian inference problem. So if we have a cosmological model that's characterized by some parameters theta, like lambda CDM or some inflationary model, or coupled to lambda CDM later. So generally what we can hope to predict is the statistics of the initial conditions, right? So the statistics of the quantum fields that gave rise to the curvature perturbations, and then later how a given initial density field or a given curvature perturbation evolves into the final observed density field, right? So basically, in the Bayesian language, we have a prior on the initial conditions that depends on the parameters of interest. And we then have in general, a model that also depends on cosmological parameters that evolves the initial conditions into whatever observable field that you have. For example, the observed CMB fluctuations or the observed galaxy density field in some volume. So the idea of field level inference is basically to just solve this inference problem fully. So we begin by, okay, so I'm going to talk about galaxies, right? This is a workshop on galaxy clustering, so appropriate. So obviously galaxies, we observe them as discrete tracers, but we can, for simplicity, put them on a grid, assign them to a grid to get a density field. We can talk about what loss of information or not loss of information that means. But let's now think of really a galaxy density field on a grid. I subtract the mean also because we can never predict the mean. It's not so interesting. We're interested in fluctuations. So then I end up with, to get my desired posterior of the cosmological parameters, I take the product of the prior and the likelihood, which is now a likelihood of the observed galaxy density field given my forward modeled, for example, matter density field, right? Or biased tracer field more generally. Yes, yes. So I mean, this is, you could replace this with zeta or R. Yeah, I'm thinking of delta n as the linear density field, right, that comes out of class. Or rather, the prior has a diagonal power spectrum given by that from class. It's of course a good question. What if you have multiple initial conditions field? Isocurvature perturbation could be straightforwardly included. I'm going to ignore them in this part. So basically, a field level inference is trying to, the aim is to infer this joint posterior and then eventually marginalize over the realization of the initial conditions, which we typically don't care about, and get the marginal posterior for the cosmological parameters. So there are several challenges. So you might ask, why don't we do this all the time like this? There are several challenges. So the first challenge is that you need expression for this field level conditional probability, right, of galaxy density field. So this is a very high dimensional object in general, right? So if you think of this as a Gaussian with some covariance, the covariance has a dimensionality of your grid's size, so it could easily be a million dimensional million-dimensional matrix, right? So that's just the dimensionality, but we also have the physics problem of how we model the entire galaxy density field. And then, of course, the second step is we need to, we're not interested so much in what the cosmological parameters are given some initial conditions, which we don't know. We're interested in the marginal posterior, right? So then we have to marginalize over this million-dimensional field. And this is challenging, and this is why this is not the standard approach in cosmology. So, but I'm gonna go forward and follow this approach. And the idea will be to solve this integral via high-dimensional Monte Carlo sampling, using Hamiltonian Monte Carlo, for example. And then doing the marginalization numerically, explicitly and numerically. So the approach is really conceptually quite clear. So if you have if you have a volume of interest, say from a galaxy survey, and you have a range of scales of interest up to some k max, then the problem becomes finite. You can put everything on a lattice, where the size of the lattice is set by your survey volume, and the resolution is set by the Nyquist frequency of. So you want to make the lattice sufficiently high resolution that your Nyquist frequency is larger than your Kmax. And then conceptually, it's quite simple. We draw initial conditions from the prior for a given state of cosmological parameters. We forward evolve using gravity and incorporate galaxy physics. We'll get to that. Then we evaluate the likelihood at the field level, and just do this in a sampling chain. And so the result of this is samples from this joint posterior, right? From this joint posterior. And as usual in MCMC, if you just ignore this parameter direction and just look at the samples of this guy, you automatically get the marginalized posterior. Good, so there's, again, a lot of interest in this recently, driven by mostly just the idea that you can get more information or all the information, but also by technical advances in the sampling regime and automatic differentiation and things like that. So here's an example on mock data done by Julia, my former postdoc, now at LMU, as a group leader. So basically she generated a mock data set that includes noise and then ran an inference chain using that same model. So there's no model mismatch. And what you see, so the observation is fixed, and you see here a visualization of the posterior on the initial conditions, right? So this is consistent with a Gaussian random field, but of course with much lower variance because it's conditioned by the data, right? So you can see that the large scales fluctuate relatively little, and the small scales fluctuate a lot just because of the signal to noise. Basically, you have lots of signal to noise per mode on large scales, little signal to noise on small scales. And this is the basically the mean inferred final density. So you can see this is not Gaussian. This is because if we use the nonlinear forward model, this is representative of the actual LSS. Good. So well, so basically, yeah. So let's defer that. Because now we come to the model, and the model really links basically likelihood and this delta forward are intrinsically linked. You can't cleanly separate them. You really have to have a joint model. And this, of course, is in general very complicated. Galaxies are nonlinear objects. We need to somehow marginalize over the unknown physics of galaxy formation. And we'll see that later that this is puts field level inference puts very stringent requirements on the forward model. So our approach is strictly to use the EFT of LSS. So to incorporate all the possible dependencies of the galaxy density field on the initial conditions into into the model. And the way we do this is we introduce an explicit scale lambda in the initial conditions. And the idea will be to sample the modes that are below lambda explicitly and marginalize analytically all the small scale modes, incorporating their possible effect on galaxy clustering. Right? So we this is basically, you can think of it as Wilsonian renormalization approach, except that usually in the Wilsonian approach, at the end you send lambda to infinity. In our case, because we need to evolve these modes explicitly, we have to keep lambda finite, right? We'll pay a huge numerical price if we make lambda too large. So that's kind of a balance one needs to strike, is to have lambda larger than your k max in the analysis, but on the other hand, if you make it too large, you'll waste a lot of effort. Yes, exactly. Right. So the idea is, okay, we marginalize out analytically the modes above lambda, and that will introduce effective bias terms in the model, and it will introduce effective noise, which then is our likelihood. No, I mean, it's the model can be evaluated for any lambda, right? Yeah, exactly. So here's the thing, right? So we have some finite scale lambda, and think back to the Wilsonian approach. Of course, our coefficients, the counter terms, make reference to the scale lambda. So they will run with lambda, but in a calculable way. So that's a good thing. That's something we're working on right now, is to actually compare the running we measure with the theory prediction, right? So it's another consistency test you can make. But so basically, the idea is we incorporate the small scale modes that contribute to galaxy formation into bias coefficients that multiply operators that are functionals, nonlinear functionals of the filtered initial density field, right? So this is clearly something we can evaluate numerically once we know how these operators are to be constructed. And that is what the EFT gave us. I mean, this is what we know now for about 10 years, is the complete set of bias coefficients at a given order in perturbations. Yeah, Matt. Right, right. Yeah, so you get higher derivative contributions that are not controlled by the scale of the tracer you're looking at, but a spurious scale, 1 over lambda. No, but k is much less than, or significantly less than lambda, right? Right, right. Well, I mean, they're all the higher derivative counterterms you would have anyway, but they're enhanced by 1 over lambda instead of whatever r star of the tracer, right? So we empirically we find that lambda of order 3/2 k max is reasonable. I mean, is good convergence. This also agrees with a paper that Massimo and company put out on looking at the renormalization of like analytically looking at the renormalization of bias at one loop order, and they also find that this is running goes away when you choose roughly at the 3/2. So other data. Well, basically, this is the renormalization story, right? So basically you have different choices for how you subtract the UV modes in your loop integrals. I mean, there are no loop integrals are basically done in the forward model at the grid level, right? That's how we do the loops. In standard calculations, you do them semi-analytically, right? And there you have different choices for what you're like. And yeah, K is always the external K mode here. I mean, I'm writing X, but you could replace this with K, of course. The external K mode, K is always less than some K max. That is less than lambda. So in the usual approach, you make lambda very large. In our approach, it's more efficient to have lambda as small as possible, but the end result should either way not depend on lambda, right? Yeah, I mean, basically the forward model follows all the modes up to lambda, right? And as you do nonlinear operations, you have to zero pad the grid in order to avoid aliasing, right? So your grid size grows as a function of lambda and as a function of the order you compute in. And the scaling with the grid size is basically, n cubed log n. That's the general cost. So but the area where we can really still improve a lot is the sampling efficiency, right? You know, requiring fewer model evaluations per effective sample. That's, I think, where we can probably gain the most. But let me go on because there were so many questions on this. So let me go, maybe I'll become more clear. So as I said, the small scale modes don't only, so these bias coefficients basically capture how small scale perturbations respond to large scale perturbations, and hence how large scale perturbations modulate the galaxy density and galaxy formation. But there's also noise introduced, right? So you cannot predict whether a galaxy forms at a given location purely in terms of large scale modes because it depends on the specific realization of the small scale modes in that region. So when you integrate out the modes, you also automatically find that you that you need noise, and you can use that to calculate the likelihood of galaxy formation given the large scale mode. So this was a paper, the result that we first did with Giovanni Cabas in a paper that Massimo also mentioned. But I'm not going to go through the details here for time reasons, but basically the key point is the following. So this noise field epsilon that we have to basically also integrate out, it arises from a superposition of many small scale modes, right? Lots of small scale modes above our scale lambda. And these are superposed locally in real space because galaxy formation is local, right? So you have a local superposition of many small scale perturbations. This means, first of all, the central limit theorem tells us that eventually this epsilon has to be close to Gaussian. And secondly, that the power spectrum of this Gaussian field has to be, constant, white noise at low k, because it's, or in other words, asymptotically a Dirac delta in real space. And with these statistics known, we can then compute the likelihood, right? So formally, we integrate out epsilon, it's a Gaussian field, and we end up with a Gaussian likelihood, which is the one that Massimo already introduced. So that's the basic idea. So the EFT not only tells us how to compute endpoint functions, but also the likelihood of the galaxy density field mode by mode. I should say that, okay, so these BO, or in general BO of lambda, but we keep lambda fixed, are free coefficients that we have to jointly infer with cosmology, and similarly the statistics of epsilon are free coefficients that we also have to jointly determine. Okay, so turning to first results, again, I want to get to new physics also, so I have to be a bit quick. So the first case we looked at is inferring AS, primordial power spectrum amplitude, or equivalently sigma 8, from a tracer amplitude, from a tracer catalog, sorry, with unknown bias, and fixing all other cosmology. So why do we do this? First of all, it's very easy to implement, right? We just have to rescale our initial conditions. And second, at linear order, we have a perfect degeneracy between the linear bias and the amplitude. So we know from the beginning that nonlinear information will be essential, right? So the power spectrum will not give us any information. And this is basically where it gets interesting for field level inference. So last year, we put out this comparison between field level and power spectrum plus bispectrum using the same forward model, same scales. And we were able to compare the two by using what's called simulation-based inference. It's a new technique in the field that came out of basically the advances in deep learning. So basically, we're comparing the posterior of sigma 8, marginalized over bias and initial conditions, given the entire field, and given the field compressed to power spectrum and bispectrum. And we found a significant improvement in the field level over power spectrum and bispectrum by a factor of 2, 3, or even more, depending on what halo sample we looked at. So these things are expensive to do. We were not able to scan through a large number of halo catalogs or Kmax or configurations. So it's a heavy machinery, and we only had these few data points. But obviously, this generated quite a bit of excitement, controversy. So there's, things get complicated when you go into the details about this comparison, right? So here we chose the third order bias model in the forward model, but the bispectrum only constrains second order coefficients at leading order. So we're kind of penalizing the bispectrum. Really, one should include the 4-point function. And we also didn't include non-Gaussian noise in the forward model because that's challenging to do at the field level. So, okay, so there's some caveats to this comparison that one could point out. There's another interesting comparison that was done in the context of the blind data challenge organized by Elizabeth and others. Here again, thankfully, the organizers enabled us to do the same kind of comparison where we only infer sigma 8. And this is the comparison between field level constraints, power spectrum and biospectrum constraints performed by Misha Ivanos with his pipeline, and power spectrum only emulator based, hybrid EFT based expansion. And so you can see here again, the power spectrum is very poor at constraining this, which is expected. But again, we see that we yield quite a bit of improvement over P plus B, even when P plus B goes to higher K. So here, this was not the same model used in both, not the same scale cuts. So it's a different comparison, but yeah, that's the result we got. One thing you might wonder while you're doing this million-dimensional inference, do you really believe your error bars? So we've done, we run multiple chains, we do Gell-Mann-Rubin statistics, and so on, compute correlation lengths. We think we have more than 100 effective samples, but yeah, it's in general a legitimate concern. So fortunately, the Beyond 2-point challenge also provided 10 independent mock realizations, and Min, my former student who led this analysis, he actually did the inference, field level inference on the different catalogs, and you see here there's no evidence for underestimated error bars. So that's reassuring. Okay, so so we have this evidence for a lot more information within the EFT from galaxy clustering. So where does the information come from? And this is really where I'm connecting to Massimo's talk. So here in this case, I will take a simplification. I will assume that we have zero noise, in which case this likelihood becomes a Dirac delta. And then we can perform an integration of the initial conditions analytically because basically we have this high dimensional Dirac delta that fixes all the modes of the initial conditions in this simplified scenario. It really only fixes them if we set lambda to k max, but this is probably not an important constraint in this, although it's worth looking at. So basically you get this, right? So you get, you perform this integral over the initial conditions. The Dirac delta sets the initial conditions to the inverse of your forward model. So you have to perform an inverse of a field level forward model, and you get this Jacobian. So this thing is, in detail it gets complicated, but formally we can write it down, right? So you just evaluate the prior, the Gaussian prior, on the inverse of the forward model. And now you can expand this in orders of perturbations and see what you get. One interesting result that you get is if you plug in a linear forward model here, just say my galaxy density is B1, some effective bias coefficient times the initial density field. This thing, the inverse is also linear, right? So this thing is just the galaxy power spectrum, right? You just get delta G squared over B1 squared P linear. And this is another nice way of seeing that if you have a linear model and a linear Gaussian random field, all the information is in the power spectrum. So now we expand this inverse forward model around the linear solution and perturbations, and we get a bunch of additional terms. And what you can see is that effectively, I'm summarizing this lengthy derivation, is that as you add more terms to your forward model, so you go higher in perturbations, you go, for example, you do a Lagrangian forward model, you have all the displacement terms. Each new term in the forward model adds a new specific statistic to the posterior, right? So you can think of if I have a forward model at second order, the EFT, all the EFT terms at second order, then you get power spectrum, bias spectrum. If you have go to third order, you add the trispectrum and so on and so forth. So in this way, you can think of field level inference as just being, let's say with sufficient compute power, it's just a very simple and direct way to systematically include higher and higher order endpoint functions. We don't have to do additional specific modeling, additional covariances for every higher endpoint function. It's all built in as soon as we add higher order terms to our forward model. So here, the difference to Massimo was really focusing on the likelihood of at the field level. What Giovanni in his paper with Marco did and I did in my paper was to look at the maximum a posteriori value of bias coefficients and sigma 8. So this is really something where you can concretely compare, right? You get directly the desired parameter posterior. So things get very cumbersome. I'm not going to talk about this. But one more thing I wanted to mention is that, so this first comparison I showed, we went to third order in the bias expansion, but we use an LPT-based forward model, which means we have displacement terms that correspond to moving the fluid from initial conditions to final conditions at all orders. And turns out that these displacement terms are precisely those that yield information on sigma 8 because they don't come with new bias coefficients. They have coefficients fixed by the equivalence principle. So it's kind of, everything working in our favor in the sense that we have all the terms we need that really give us information on sigma 8 at all orders. Of course, we don't have higher order bias terms, right? So you could say, okay, at fourth order, we have all the displacement terms, but we don't have fourth order bias. What you can also show in this approach is that what's the impact of missing terms? And it's basically a scalar product of the missing terms with the ones you have. And it turns out that the scalar product of displacement terms with bias terms is typically suppressed because they have different kinematics. So, I mean, these are all things that are a bit nebulous still, but there are things that point in the direction that higher endpoint functions are playing a role here. Yes. Not really. Dennis has results on this, right? Where, uh, I mean, there's quite a bit different cross correlation between. Well, visually, certainly in the map you won't see. I mean, we're talking about constraints of 3% versus 5%, right? That's the kind of on sigma 8. That's the kind of stuff you will not see by eye in a map, right? Yeah, we can discuss that in more detail. I don't think it's 1%, but um, yeah. So basically, here there's a few arguments for why higher endpoint functions could play a role, but it's of course, you know, to really do it, we would need to include them in explicitly, right, in our endpoint function based analysis. So so this gets pretty complicated. So I thought maybe it's worth looking at a simpler scenario. Let's just look at the simplest possible second order coupling I could have, which is just a local coupling, right? So I take my linear density field and add the square to it, and no other nonlinearities, and Gaussian noise, right? So this is work done by my current student, Ivan Nikolats, and the idea is let's compare field level inference with endpoint functions for this case and see what comes out, because it's infinitely faster to compute, so we can run and you have fewer free coefficients, so it's much easier to explore. And so this is the result of the marginalized constraint on the second order coefficient, right, which is kind of our analog of sigma 8, if you want, for a fixed maximum scale of 0.14. And the two different curves show SBI again, and which should asymptote to the true posterior, and the Fisher calculation, which is kind of a lower limit on an upper limit on the information, lower limit on the error bar. And what's interesting is that indeed, if you go to the fiducial value of 0, b delta squared, which means you're really perturbing around the Gaussian field, then indeed field level and power spectrum and bias spectrum give exactly the same information. And then as you turn on the fiducial value, as you make the field more non-Gaussian, the information gain in the field level increases, right? So the power spectrum, the P plus B constraint is a factor of, at this pretty large value of the coupling, is a factor of 2 worse than field level. So this clearly shows also that it's not just about, one of the key points that matters also is what space in the model you are, whether you're closely to perturbing around the Gaussian or whether your field is highly non-Gaussian. And what highly non-Gaussian means is, of course, matter we can debate. Yeah. You measure power spectrum and bispectrum in this, right? And we can the model you can compute either analytically or just by averaging over realization. Yeah, we sample a linear density field and square it. You have to enlarge the grid, of course, to avoid not and add noise. And, right, right, right. Oh, this is a comparison, apples to apples comparison. Right. I don't see what's misleading here. I'm just saying I take an example that's the simplest possible non-Gaussian field, and I see what the information gain is in field level inference versus endpoint functions. That's all I'm saying. Right. So I think I had the feeling I'm losing a lot of the audience here because it's like 3 people interested in this question, and so I would really like to get to new fig. So if we could postpone this discussion maybe to a specific discussion because it gets really technical. So right. So what if we include higher endpoint correlations? We do it in a compressed way by basically correlating powers of the data, which is what you would expect. Um, you know, that should be the complete statistics at higher orders in this case. And what you can see here is that as you go to a higher order, so the orange case was basically is P plus B, and then blue is adding the trispectrum and successive higher endpoint functions. And you can see that indeed, the higher endpoint functions recover the information, but the recovery gets worse and worse um, as you dial up this non-Gaussianity of the field. So the interesting question is what expansion parameter is controlling this convergence of the information in the higher endpoint functions, right? And so this is, I think, still an open question. Yes, everything, yes. Right, so you can't even, I mean, this is, if you want, is not even the EFT, it's just a case of you have a process generating a non-Gaussian field, and how much of that information on the coupling constant is captured by low order correlation functions. Right? Yeah, but it's in the model and in the inference, so it's it's just a self-consistency thing. No, it's the model and the inference are using. I mean, it's the same. It's always the same consistency. Oh, you're saying with the scale at which the density field becomes nonlinear varies, of course. Yes. Right. No, no, absolutely right. I mean, I'm saying basically that if we go to sufficiently large values here, indeed, we're in the non-perturbative regime. Right. Indeed. No, this model, the ground truth only has second order coefficients, right? We're comparing always a model and inference, data and inference are generated from the same process. There is no UV physics that we're marginalizing over here, right? This is purely about the statistics of the field. No, the answer, short answer is no, because there's no UV modes here, right? There's no need to renormalize, basically. Okay, so I definitely skipped the BIO part. So yeah, so basically, summary is that, field level inference, well, the nice thing about it is that it's guaranteed to be optimal if your model is correct. So we see a significant gain in sigma 8, like we discussed. Also, there's gain BAO reconstruction that come from very different sources. We can discuss about the BAO if you want later. And we have these analytical and toy model results that kind of are pointing us in the direction where the additional information is coming from. And I would say the evidence points toward it being a finite but not necessarily small set of endpoint functions that are relevant. And another corollary of this is that if you go beyond the regime of perturbation theory, which is not our goal, but is other people are pursuing that approach, if you do field level inference, you really need to describe all endpoint functions. So that is not going to be easy, and I think it's in fact going to be very challenging. Okay, so I really wanted to talk about some new physics because this workshop, to me, the most exciting part about this new workshop is the new physics. So I have three topics. I don't know. Well, lunch is at 1, right? So. Well, stop me whenever. So maybe I'll go. Yeah, I'll go about it through the dark energy. Probably this will generate even at least as much discussion. So anyway, so back a few years ago, well, more than a few, 2017, I was thinking about, okay, back then everything was pointing to W is consistent with -1. I was thinking, does that really prove that dark energy is lambda, given that we typically, when we constrain W from observations, we always assume it's slowly varying, right? We assume oftentimes a constant W or constant plus a slope. So given that we really only measure an average W, how can we really conclude dark energy is lambda when W is consistent with -1? Turns out for canonical scalar field, yes. So I write the dark energy action as some P of phi and X kinetic term. So for canonical scalar field X plus V of phi, you get, of course, that W is this expression. So if this can only be -1 if the potential, if the field is frozen and you're basically at lambda, right? But in general, it's not true. So if you go beyond a standard kinetic term, you can have cases, what's known as K essence. So it's, you add an X squared with some mass scale to the action. And if this potential that's multiplying this has oscillations, like in these monodromic stringy scenarios, then you can have an oscillating equation of state, right? So this is just a toy case I showed in my paper where, you have W oscillating quite significantly. And if you integrate over time, or if your model is a constant W, you will infer that W is close to -1, but in fact it's not, right? So now many of you will ask, well, yeah, perfect. So at the background level, this is all good, but the perturbations have a problem because typically CS squared, the sound speed squared, becomes negative when 1 plus W becomes negative, right? Yeah. Yes. Yeah, you violate, in general, these theories violate the null entry condition, right? So, right. So I think this is related to this. So there was a nice paper by Criminelli et al. In 2009 who showed that if you're very close to 1 plus W equals 0, right, then your K squared, so CS squared will typically have the wrong sign, so will lead to exploding perturbations. But you can cure this if you include the next order derivatives. Think of it as an EFT with some cutoff scale, and so there should be higher derivative corrections to your EFT also. Yeah, exactly. So it's related to the ghost composite, right? So they argued that okay, you have now a theory with a pretty low cutoff, but it's observationally allowed, right? So and so recently we went back to this. So with Sam Goldstein, who was a PhD student at Columbia, and Marco Celoria, who is now in Milan working at a HPC institute, but visited MPA some years ago. So Marco came up with an example scenario that is amended my naive and wrong scenario here. Basically, it becomes slightly more complicated, but essentially, yeah, you have the standard k-essence term, and you modulate it with an oscillatory function. Okay, so maybe not the prettiest model in the world, but it turns out that in this scenario, you can get oscillations of W around -1 that are of order 0.1, so interesting amplitude with, sufficiently small sound speed that it satisfies all the tachyonic constraints. So yeah, and so this was due to Marco, and then with Sam, Sam went back and looked at DESI now, right? So there's a totally different motivation, which is the evidence for non-constant dark energy from DESI. So we still looked at this wrong model from my paper, but I think it will be qualitatively extremely similar in the correct, theoretically correct paper. So basically what you have, so we have an effective omega dark energy, and we have this tilt in the potential, which you can think of as the mean W. And then we have 3 additional parameters, which is the amplitude, frequency, and phase of the oscillations, which we all infer jointly. So this was actually non-trivial to get to work in an MCMC chain. We were very careful to exclude observables that are sensitive to perturbations because the perturbations are non-trivial because we have, dark energy has CS of 0, so it will have perturbations that are non-trivial. So we isolate the geometric information from the CMB. I think Zach explained this very nicely last week. And so here are the, here's the constraints just from DESI plus CMB. This is the angle averaged distance, and this is the Hubble distance. So the BAO scale in the line of sight direction. And so the BAO scale in the line of sight direction is a time derivative of dA. It's 1/h, right? So that's why you see stronger oscillations here, right? So this scenario will, of course, be more prominent in things that are, probing time derivatives, basically. So this is the preferred model in that space. The model changes completely once you include supernovae. Maybe not surprising. So the black line was the just DESI plus CMB, and then if you include supernovae, it becomes the red or the blue curve. So it fits pretty well. In fact, this fit quality is similar to DESI, the DESI standard W0 WA case. So if we say, okay, let's fix the mean W to -1 because that also makes the theory model nicer, then there's really only one additional free coefficient compared to DESI. So and you get roughly the same fit. So I think it's not such a bad model. Yeah, this is the full constraints. Let me skip over this in interest of time here. Just this is basically what I wanted, I had in mind in the first paper, is that we would put constraints on the amplitude of oscillation. Apologies for the weird orientation, but I wanted to, so this is A, right, the amplitude of oscillations. This is as a function of frequency, and you see if you, okay, so just DESI plus CMB, there you basically have no constraints. DESI, CMB, and Pantheon, you get this constraint curve, right? as a function of frequency. So it's another nice case where we can just look for this monodromic case as a function of frequency. And then if you use DS supernovae, as is well known, they prefer a stronger evolution of dark energy, and you get a non-zero evidence, right? So in this frequency range, they prefer a non-zero amplitude. And Sam also made these very nice figures of the reconstructed W, which is the top panel, and effective quiescence potential, which is the bottom panel. And yeah, so basically here is kind of what you expect if you have no evidence, right? It's fluctuating around -1, but DS, pulls it towards a non-zero amplitude. So all I wanted to, or one of the key points here is to see that this model is totally fine as we go to a higher redshift, right? It will asymptote to -1 equation of state, whereas the W0 WA becomes more and more unphysical as you go to a higher redshift, right? We know that it's not a physical model. That was dark energy, and in the last 5 or so, 7 minutes, yes. Yeah, so there will be some impact of perturbations on the matter power spectrum. I think it will be quite small because the perturbations are still controlled by 1 plus W, right? So 1 plus W is still relatively small, but potentially could be interesting. So that's future work, is to look at that. But basically, so morally, because sound speed is 0, dark energy and dark matter will basically have the same power spectrum, just with different amplitude. Right? There's no scale dependent feature. Yeah. Yeah, sure. Everything is Horndeski. Yeah. Oh yeah, right. Yes. So you have right, right. Yeah. But it was. I think you found it's like it's a percent level or less, right? Right. Right. Well, you can see it depends, of course, on which data combination you use, right? So if you use the one that is, that has the strongest evidence, I think this, is like oscillation of like 0.2 in magnitude, which is also pushing the model a bit. Um, but yeah, at low redshift. Yeah. So I mean, DESI will, the BIO will improve. I don't know about the supernovae. Satya is not here, but I don't know if anyone else knows. But yeah, BIO will for sure improve. So yes, yes. I mean, there's also a bit. I mean, we found, or Sam found, that one of the data points seems to be driving. One of the DESI LRG points seems to be driving this, which of course is not, doesn't point toward it being maybe a physical thing, but we'll see. I mean, I don't want to say anything strong about this. Okay, let me try to cover this as well because I think it's really neat. I think that the PBH is also very neat, but maybe you can ask me about it. Anyway, so a completely different story. Now I'm moving beyond galaxy clustering to galaxy shapes. So galaxy shapes, to the more theoretically minded in the room, basically we're not only treating each galaxy as a point in space, but we're measuring its shape by the second moments of the image, and basically you have a 2 tensor now, right? So a galaxy shape is a 2 tensor, it's a 3 tensor projected on the sky. So 3 tensor to 2 tensor projection. I mean 3D tensor to 2D, sorry, it's always a spin 2 thing. And it turns out, I mean, one of the nice things about tensor fields is that you can probe parity, which you can't do with scalars. And so the idea of this paper, led by Toshiki Kurita, is to see what kind of primordial parity violation we can probe. So this is a little bit preempting Jamin's talk tomorrow, but let me just give it a lightning introduction. So if you start with curvature perturbations, then the only way to generate parity violation, or the leading way, is in the 4-point function, because you need 3 vectors to have something with a handedness in space. And so that means you're going to the 4-point function, which we can then always write in terms of this Jacobian, right? So this K1 dot K2 cross K3 is the unique triple product that will generate something that's parity sensitive. And so now in LSS, we're generally in the regime where we probe primordial physics in a squeezed limit, because we're trying to extract information from pretty small scales. That's, you know, pretty small scales being what galaxies are sensitive to, and then large scales where we observe them. And the 4-point function has two squeeze limits. So one is the proper squeeze limit, is where you make, sorry, is this, no, this way. So we have 4 K modes that have to add up to a quadrilateral, and so this mode is a K long that's much smaller than the 3 others. And one thing you can notice here is that this basically looks like a bispectrum, right? If I send KL to 0, it's a triangle. So we're back to a bispectrum, and we know a bispectrum is not sensitive to parity. So we already know that in the squeeze limit, the parity signatures here have to be suppressed. And the other regime is the collapsed limit, something like this, where now the small mode is an internal mode, right? So it's a diagonal. Again, same story. This is kind of a bispectrum, but so anyway. So yeah, so it turns out that the shapes are particularly sensitive to this kind of configuration, collapsed limit. And when do you have an enhanced collapsed limit? When you have multiple fields present, right? And so the physics case we're looking at is you have a chiral U1 field that couples to the inflaton via some, you know, FF dual type term. And you need the field to be chiral, because otherwise the parity alt statistics will just cancel out. Good, okay, so Toshiki went ahead, and so it turns out that, so this is a paper we wrote in 2020, where you can show that you can, I mean, it's not surprising, right? You can write an EFT also for galaxy shapes, including basically incorporating that now the symmetries are for a 3-dimensional 2 tensor instead of a scalar. And so Toshiki went ahead and computed all the loop contributions of a primordial trispectrum to galaxy shaped 2-point functions. And from there are new divergences appearing, which force you to add a counter term, which is analogous to the scale-dependent bias you get for primordial non-Gaussianity in galaxy shapes. And again, so it turns out that the collapse limit is the interesting signature. This is the relevant loop integral. And then Toshiki went ahead and actually ran simulations with this type of initial conditions generated, ran full n-body simulations, measured the halo bias in these, and measured the coefficient of the scale-dependent effect. And so what's happening is, so here you see the power spectrum of the helicity 1 part of the, so now the shape statistics have helicities. You have 0, 1, and 2, and only 0 is like a scalar, right? So it's not parity sensitive, but 1 and 2 are parity sensitive. And he confirmed nicely that we get this enhancement. And basically the enhancement is, so you have this what did I call it? I mean, so we call it in paper, we call it psi, this spin 1 field, and you get basically that the P shape on large scales is proportional to P psi, which if we assume that scalar invariant goes as k to the minus 3, right? Compared to the standard Gaussian part, which goes as k to the ns minus 1, right? K to ns. So this is a very strong enhancement on large scales, k to minus 3. Yeah, measured the bias coefficients and did a forecast for how this particular model could be constrained by DESI shapes. So you use galaxy redshifts from DESI and shapes from their imaging counterpart, and should be quite competitive. So I think it's neat because in this model, if it's there, it means that the galaxy shapes on large scales are really tracing this helical U1 field. So you kind of have, it's also known as fossils. You have this remnant of the primordial vector field that now galaxy shapes trace if you have this particular type of coupling. Yeah, and the final topic is PBHs, but I think I'll stop here, and if people want to ask about PBHs, I'm happy. There's videos, by the way, so please go ahead. And there's something interesting that goes beyond standard EFT. People are interested, but I'll stop here. Thank you. Yeah, so no, the large scale vector field is modulating the small scale perturbations. Yeah, except that the large scale vector field, of course, by symmetry cannot directly correlate with scalar perturbations. So you have to have glue two of these together, right? And that leads to that's the collapse limit, right? So you basically, in terms of a Feynman diagram, you have like R here, and then there's like this psi field, yeah, psi field coupling this way, and this coupling has a characteristic signature that can be extracted. We measure the alignment coefficient, right? So the EFT can predict what the shape is, but it cannot predict the coefficient, which is this B minus squared. Yeah, just like in the usual PNG case. Yeah. Yeah. Probably it is. I'm not. Yeah, I'm not very deep into that part of the literature, but I think it's that. Yes. No, you need the yeah, the effect is due to perturbations in the chiral field. Yeah. So it's not high derivative, but the dimensionality, I mean, you can work it out from here. I don't, you know better than I what this is. So there's Shira Ishii, and has, I think, worked a lot on this, if you know this. But I can point you to the reference. I think, I mean, we have to push the coefficient quite a bit to make this visible, right? So this is the dimensionless coefficient in the template, which is, non-trivial relation to the model, but is like 10 to the 5 because this is always, you know, if you have a primordial trispectrum, dimensionally, you will always need something like 10 to the 5 to see it, because that corresponds to FNL of order 1, right? Because, yeah. You mean the covariance that's in the like, that is a free parameter that is inferred jointly with the bias coefficients. So actually, most of the analysis, we're effectively fixing it, because it leads to extremely long correlation lengths. But yeah, in principle, I mean, that's something we need to work on, but in principle, it's jointly inferred. Yes. I mean, you can put a prior, of course, you can always put informative priors on the EFT coefficients. Um, yeah, so we expect it to be of order 1 over n bar, this power spectrum of the noise, but that's not, you know, it will certainly have some variation around that. Yes. Yeah, so this is what Julia Stadler is now working on. So we have a working model, which is, yeah, it might be in there somewhere. We have a working model that is validated at fixed initial conditions, but we are now only starting with inferring, you know, also doing the field level sampling. But morally, it's quite easy, right? Because you just transform the entire field to redshift space. So you don't have to do any expansion there either. You can do it. If you have velocities, you can do it non-perturbatively. Uh, No, no, absolutely. So this is we have a couple of earlier papers with Lisa Chisari and Yuko Urakawa where we looked at. So basically, if you go away from parity violation and really the simplest probe of PNG from shapes is really, you know, anisotropic structures in the squeeze limit. Exactly, spin 2, for example, the spin 2 shape you can constrain. Yes. I think actually Toshiki might have observational constraints on that. I think he derived observational constraints, but I'm not sure if he assumed the collider shape or something like local, which of course is incorrect in this case, strictly speaking. Vector modes, like how are they like? I mean, these are vector modes, but they're basically fossils imprinted in the scalar perturbations. But where would they? How would they? Where would they come from? Oh, right. Um, yeah, I mean it's basically you're looking then at very small scales, right? So the question, I mean, yes, it will introduce some additional power on small scales, but how are you going to disentangle that from all the other small scale mess? That is, I think, the tricky part. Yeah, yeah. The key point is that you have this coupling of long and short modes, right? So this psi here is a very long mode. These are fully nonlinear, but this psi is a long mode, and so we see the imprint of those long modes. So if your vector field was modulated by some super horizon isocurvature modes or whatever, then maybe that could lead us. Well, I mean, we want them to be larger than the nonlinear scale today, which is, and before recombination generally means super horizon, right? Oh, I see. Phase transition at redshift 1. Okay, that I didn't, okay. No, that, yes, yes. Yeah, I mean, there was also this self-ordering scalar fields. I don't know if you know that story. That seems related, right? Um, yeah, exactly. So you have things entering the horizon and then they reconfigure. And yeah, I mean, I think, right. But then you would have gravitational coupling only, right? Or are you thinking, yeah. So that will be, I mean, we can discuss. I think it will be very small, but one can, it depends basically on the energy density in these modes. Yeah, right. So, I mean, here we're gaining. So there's several. What's nice about parity odd is that you have no contributions from standard curvature perturbation, right? I mean, there's if you have no other source of large scale parity violation in the universe, then there's no noise here, and the only, I mean, there's no cosmic variance. The only noise comes from intrinsic galaxy shape, small scale randomness, which of course has equally generates even and odd parity. So that is the noise, and that is a bit less than galaxies because ellipticities are not one, but so it's maybe an order of magnitude less than the noise in galaxy clustering. But then the question is, how big is this alignment signal? So the alignment coefficients are also typically less than galaxy bias coefficients. So, but this is a totally underexplored area, and really, I think it's, if you're looking at galaxy clustering, you might as well think about shapes too. So you have chirogravitational waves, you mean? Yes, so then you would also generate the same statistic and also scale invariant, so they two will look exactly the same on large scales. Yes. But so you might see a difference in the redshift dependence though, because if tensor modes obviously have a non-trivial evolution when they enter the horizon, and so that is expected to also appear in the alignment signal. So then you would need the redshift dependence. So both would be K2 minus 3, right? So just for reference, if you can think of it as looking at the CLEB of galaxy shapes, or in the CMB, you know, polarization, it's the analog, but now galaxy shapes. So this is the statistic. I mean, there's one of the statistics Toshiki is looking at. If you generalize to 3D, it's a bit more complicated. You have three helicities, but